reaction that happens in our oceans. Right now we have calcium carbonate and H plus ion that are in equilibrium in the ocean. Whenever you have water, you're going to have some H plus. And the calcium carbonate is going to be our corals, any of our shellfish, so oysters, clams, geoducks, pteropods. All of those are going to have calcium carbonate in their shells. And when they come in contact, the calcium carbonate sometimes dissolves and turns into this. So since I care about life in the ocean and I care about the health of the ocean, also because it's a carbon dioxide sink for us, so even if I don't care what's going on in the ocean at all, it affects us. So I care what influences the equilibrium of this reaction. What influences to what degree the calcium carbonate dissolves or to what degree the calcium carbonate stays. So what affects the equilibrium? An equilibrium is going to be the balance that a system achieves between products and reactants. Equilibrium is dynamic. Dynamic means it's going to be continuously changing. So your reactants will always be turning into products and your products will always be turning back into reactants. But when you look at a system that's equilibrium, the amount of products is constant and the amount of reactants is constant, so you can't actually see the change that's happening. It's happening at the same rate. So that's why we say reactions in a closed system don't stop. They reach a dynamic equilibrium. The rate at which reactants turn into products equals the rate at which products turn into reactants. So I'm going to use red to represent reactants. This will be a reaction over time. I start with a lot of reactants, and at first they're being quickly used up because we know in kinetics reactions happen faster at higher concentration, and eventually they stop changing. The opposite happens for my products. I start with 0 products, and at first they're being formed very quickly, and then they start to form more and more slowly. Basically, they're not changing. So I have some kind of equilibrium achieved between my products and my reactants, where I can see most of my reactants turned into products. So this is considered a product-favored reaction. An example of a product-favored reaction would be calcium carbonate and acid. It is going to react, it is going to dissolve. Most of your calcium carbonate will dissolve. So this is a product-favored. But meanwhile, let's see another scenario. We could have reactants turning into products, and at first it changes quickly and then not so fast. Opposite for the products, like that. And again, I've achieved equilibrium, but this time I have most of my reactants left. This is reactant favored, and an example of a reactant favored would be calcium carbonate and water instead of an acid. So if the calcium carbonate, like chalk, if I took a piece of chalk and I just threw it into a glass of water, a little bit will dissolve, but very, very little. I'll keep most of my calcium carbonate as a reactant. Okay, so we can see the two differences, and one big thing we want to notice is equilibrium does not mean equal. It does not mean I have the same amount of reactants as I do products, but it does mean the rate at which the reactants turn into products is equal to the rate at which products turn into reactants. So KEQ is the way we measure equilibrium. It's going to be, KEQ is going to be our constant, so it's not going to change. If I have one reaction, I will have a KEQ for that reaction, and as long as the temperature is constant, the KEQ will be constant. Change the temp, get a new K. So the way I write KEQ is it's going to be the concentrations of the products raised to their powers over the reactants raised to their powers, raised to their coefficients, sorry, not power. And what this is representing, my A plus B goes to C and D, would be, well, this is my coefficient, and this is going to be my reactant. So it could be like saying 2H2 plus 1O2 makes 2H2O. So what I say is I say concentration of the products, C raised to the coefficient of each product. Remember, brackets mean concentration or moles per liter. And it's going to be divided by concentration of the reactants raised to their coefficients. So when I plug this in, I'm going to get a value for KEQ. And that value for KEQ is always going to be the same as long as I don't change the temperature. No matter how many reactants I start with or how many products I start with, it's always going to be the same. And the reason that happens is if I start with all reactants, they'll react until they start making products, and the more products there are, the more likely they are to turn back into reactants, and so they get to some kind of balance where they stop changing. If I start with all products, same thing. At first they're all turning into reactants, and then eventually reactants are turning back into products, and you reach that equilibrium or that balance. There's a couple rules. We're going to leave liquids and solids out of our equilibrium expression, out of our KEQ expression, and that's because the concentration of liquids basically doesn't change. So if I had a 1 molar solution of an acid, during a reaction, the concentration of water is going to be pretty much the same. It's constant. But the concentration of the acid would change noticeably. And meanwhile, concentration of solids doesn't affect the equilibrium because the solid's stuck, at the bottom of your container. The more solid you have down there doesn't mean the particles are more likely to react. So the concentration of a solid isn't going to change either. So we leave those two out. So if I'm going to write KEQ for this, I do my products over my reactants, but I'm going to leave this liquid out. So instead of putting H2O to the power of 2, I'll just put 1. And then H2 is going to be squared, it's raised to its coefficient, and O2 raised to its coefficient 1. The KEQ for this has all gases, so I get to put them all in. By the way, I can only use gases or aqueous things because I said solids and liquids are left out. So this is H2O raised to its coefficient, and hydrogen raised to its, and oxygen raised to its coefficient, 1. And down here, I have solid calcium carbonate. It's turning into calcium ion and carbonate ion. That should be AQ. I'm going to leave that solid out. So KEQ is going to equal just the concentration of the calcium ion times the concentration of the carbonate ion. And it would be over that solid, but instead it's over 1 because I leave the solid out. And I don't have to write over 1. So there we go. There are some different Ks. So KEQ is just generically saying equilibrium. But we can calculate that equilibrium using concentrations. Concentrations of a gas, how many moles per liter in a gas, or concentration of an aqueous solution, how many moles per liter of an aqueous solution. And then Kp is going to be if I have all gases, and I use the partial pressures of these guys. So if I'm going to write Kp, it's the same setup. Products over reactants raised to their coefficients. I have to use gases. So I'm going to say the partial pressure of water, that's a big P sub H2O, raised to its coefficient, squared, over partial pressure of hydrogen, raised to its coefficient, squared, and partial pressure of oxygen. All right, that'd be the Kp of that equation. Let's go ahead and calculate a KEQ. I'm going to calculate Kc because I can see I have molarities here. I have nitrogen, hydrogen, and ammonia are placed in a closed container and allowed to reach equilibrium. At equilibrium, the concentration of nitrogen is 1 molar, hydrogen 2.2, and this is ridiculous, sorry about that, 61,048. So I'm going to calculate Kc. Kc is the products over the reactants raised to their coefficients. So ammonia squared, that's the 61,048 squared, over nitrogen, which is just 1, and it's raised to coefficient of 1, right there. And the hydrogen, 2.2, and it's going to be cubed because there. So I type these in, and I see that it is 3.5 times 10 to the 8th. Make sure you type it in. Make sure that you're going to get it right when you need to get it right.